For a long time, it was thought that the entire universe was a single island of stars. This island was the galaxy we now call the Milky Way. There was no reason in the human imagination to think of anything else. The night sky appeared as a closed ceiling. The stars were fixed points. The cosmos felt small, limited, and close. That changed in the 20th century when telescopes began to resolve diffuse patches in the sky. These patches were not clusters within our galaxy. They were entire other galaxies, each one an immense system of stars, gas, and dust. Over time, it was understood that the observable universe contains hundreds of billions of galaxies. The Milky Way ceased to be the center. It became just one among many. This correction of scale is the first step toward talking about life beyond our galaxy. We are not in a privileged corner. There is no evidence that our position is special. The physics we know applies here and in any other galaxy. The observed physical constants are the same. Gravity acts the same. Light behaves the same. Matter obeys the same basic laws. If the laws are universal, the processes are too. Stars form by the collapse of gas clouds everywhere. Inside them, they fuse hydrogen into helium. In later stages, they produce carbon, oxygen, nitrogen, iron, and other heavy elements. When these massive stars die, they expel them into space. This enriched material forms new generations of stars and their planetary systems. It is not a local story. It is a cosmic routine that repeats in billions of galaxies. Life, as we understand it, needs some of these elements. Carbon to build complex molecules, oxygen for efficient energy reactions, nitrogen and phosphorus for genetic material and proteins, hydrogen for water. None of that is rare. The universe is full of hydrogen. Carbon is one of the most abundant elements. Oxygen too. The chemistry that allows life is neither exotic nor scarce. The very history of Earth reinforces this idea. Our planet formed about 4.5 billion years ago, from the disk of gas and dust around a young star. For hundreds of millions of years, it suffered violent impacts and unstable conditions. However, as soon as the surface cooled enough and liquid water became possible, life appeared relatively quickly. The oldest evidence of biological activity dates back more than 3.5 billion years. This means that, on a geological scale, life did not take long to arise. This does not prove that life is inevitable, but it suggests that in an appropriate environment, it does not need billions of years to get started. It doesn't seem like an extremely late accident. It seems like a process that is activated when minimal conditions are met. Liquid water, some temperature stability, an atmosphere that allows for chemical exchanges, and a constant energy source. These conditions are not exclusive to Earth. They are the natural result of certain types of stars and planets. Here appears an idea that runs through all modern astrophysics: the principle of mediocrity, the hypothesis that we are not special. Our Sun is a common type star. It is not the biggest, the smallest, or the brightest. The Milky Way is a large spiral galaxy, but not unique. Our position in one of its arms is nothing privileged. If none of this is extraordinary, the provisional conclusion is clear. What happened here could have been repeated in many other places. When we look beyond the Milky Way, we see galaxies with different morphologies: spirals, ellipticals, irregulars. But all of them show signs of star formation at some point in their history. Many have gas-rich regions where new stars are born. Others, older ones, had their phase of intense star formation in the distant past. In both cases, the chemistry necessary for life has been manufactured and recycled for billions of years. Time also matters. The universe is about 13.8 billion years old. Earth appeared when the universe was already mature. Before our solar system arose, entire generations of stars had already lived and died in other galaxies. That is, there were environments with heavy elements and possible planets long before us. If life had only arisen here in one specific galaxy, around one specific star, within a limited time frame, it would be an extreme coincidence. Of course, this way of reasoning does not replace evidence. It is not enough to say, the universe is large, so there must be life. Scale alone guarantees nothing. What it does do is change the way we ask the question. Instead of asking, is life possible outside our galaxy? The question should be, is there any solid physical reason to think that the chemistry of life only organized itself once, on a single planet, in all of cosmic history? A galaxy is not just a collection of stars ordered in space. It is a dynamic system, constantly recycling, coal gas collapsing, stars being born, stars dying, explosions returning matter to the medium. Each cycle adds chemical complexity. Each generation leaves the stage a little richer in heavy elements. These elements are the foundation of rocky worlds and the chemistry of life. In the Milky Way, this process is well studied. We know that the primordial gas was almost entirely made up of hydrogen and helium. The first stars fused those elements and created carbon, oxygen, nitrogen, iron, and many others. When they died, they seeded the interstellar medium with these products. The next generation of stars formed in already enriched clouds. Their gas and dust disks gave rise to planets. The important thing is that this mechanism is not exclusive to our galaxy. It is a general pattern. When we observe other galaxies, we see clear signatures of these same processes. In spirals similar to the Milky Way, we see arms filled with star-forming regions. These areas shine in ultraviolet light and in certain emissions characteristic of ionized gas. They are birthplaces of stars. In irregular galaxies, more chaotic ones, we also detect collapsing gas clouds and young stars. Even in many elliptical galaxies which seem more dim, there are traces of past star formation episodes. In all of them, matter transforms according to the same physical rules. The elements necessary for life are formed in these environments. Carbon, for example, is produced in the advanced phases of intermediate mass stars. Oxygen mostly in supernova of massive stars. Iron in thermonuclear explosions of white dwarf stars. There is no special type of galaxy for this chemistry. What changes is the intensity of the process, the pace, and the spatial distribution of the enriched material. Metallicity is a key concept here. In astrophysics, metals are all elements heavier than helium. A young galaxy will have few generations of stars and therefore lower metallicity. A galaxy that has formed stars for billions of years accumulates metals in its gas. The higher the metallicity, the easier it is for rocky planets to form. Observations show that stars with high metallicity are more likely to host complex planetary systems. This implies that many galaxies, especially those that have experienced long periods of star formation, have large regions with high metallicities. Regions where the appearance of rocky planets is not a rarity, but a natural consequence. These planets can be located in stable orbits, at distances where liquid water is possible. The so-called habitable zone is not a unique trait of the Sun. It is a range of distances that any star can have, depending on its brightness. Moreover, prebiotic chemistry does not wait for the planet to form. In gas clouds within and outside our galaxy, complex organic molecules have been detected. Simple alcohols, aldehydes, even molecules with relatively long carbon chains. These molecules form on dust grains, in conditions of low temperature and limited radiation. Then, when the cloud collapses and stars and planets are born, part of that material falls onto the young worlds. In other words, the basic building blocks of life can arrive pre-assembled. Protoplanetary disks are another supporting point. Around newly born stars, current telescopes show structures of rings and voids. These rings mark areas where material gathers to form planets. These disks have been observed in many star-forming regions within the Milky Way. If we extrapolate, there's no reason to think that similar disks don't exist in other galaxies. Where there are disks, there are planets under construction. Where there are planets, there are surfaces, potential oceans, and possible atmospheres. The diversity of galaxies also plays a role. In spiral galaxies, the mix of young and old regions creates a variety of environments. In dwarf galaxies, the processes may be more violent, but that doesn't exclude star and planet formation. In galaxy clusters, gravitational interactions trigger new waves of star formation. Each configuration adds nuances to the distribution of possible worlds. But the general trend remains. The universe is highly efficient at producing stars and with them, planetary systems. The available time is immense. Many galaxies began forming stars when the universe was only a few 100 million years old. Since then, more than 10 billion years have passed. This means that, in distant corners, there could be planetary systems much older than ours. Worlds that have had billions of extra years for chemistry to organize, life to emerge, evolve, and adapt to changing environments. Another factor tipping the balance is the robustness of life in extreme conditions, as seen on Earth. Bacteria that withstand intense radiation.
Microorganisms that live in supersaline waters, acidic environments, or at temperatures close to the boiling point. Organisms that thrive in absolute darkness, around hydrothermal vents, sustained by inorganic chemistry. If life here is not limited to temperate and comfortable environments, then the number of potentially habitable environments on a galactic scale multiplies. If we combine these elements, a coherent picture emerges. Galaxies functioning as chemical factories for billions of years. Stars that are born in enriched clouds. Protoplanetary disks filled with material suitable for building rocky planets. Organic molecules already present in the medium before worlds even form. Extremophiles that demonstrate that life tolerates conditions we once would have considered lethal. None of these factors are confined to the Milky Way. At the same time, the observable universe contains, according to current estimates, on the order of hundreds of billions of galaxies, each with billions or even trillions of stars. The Milky Way, with its hundreds of billions of stars, is a typical example, not an exception. If we consider only a fraction of those galaxies as similar to ours in size and composition, we already obtain a gigantic number of potential stellar systems. At the level of each galaxy, the next step is to ask how many stars have planets. Observations of exoplanets in our own galaxy reveal something important. Planetary systems are not rare. Almost every time we look with sufficient precision, we find planets around stars. Not only gas giants, also rocky worlds, some in regions where the temperature would allow liquid water. It is reasonable to assume that this trend repeats in other galaxies. One way to organize this idea is to use a framework similar to the Drake equation, but applied more broadly. First, the number of galaxies, then the average number of stars per galaxy. Next, the fraction of stars with planets. After that, the fraction of those planets located in the so-called habitable zone. Beyond that, the fraction that maintains relatively stable conditions for millions of years. And finally, the fraction in which life actually emerges. Each of these factors has enormous uncertainties. We do not know their exact values even. within our own galaxy, much less outside it. But we can work with ranges. There are conservative, moderate, and optimistic estimates. What matters is not an exact number, but the order of magnitude, whether the final result is close to zero or, instead, gigantic. Experience on Earth suggests that if the minimum conditions are present, life can appear relatively quickly. It did not take billions of years.
Each of these factors has enormous uncertainties. We don't know their exact values, even within our own galaxy, let alone outside it. But we can work with ranges. There are conservative, moderate, and optimistic estimates. What matters is not an exact number, but the order of magnitude, to know whether the final result is close to zero or instead gigantic. Experience on Earth suggests that if the minimum conditions are met, life can appear relatively quickly. It didn't take billions of years. It took advantage of an early window of stability. This allows us to assign to the probability of life's origin a value that, while uncertain, is not ridiculously small. We are not talking about an event that needs an entire universe to occur just once. A process that is activated in many compatible environments seems more likely. Here, it is useful to distinguish between two levels: simple life and complex life. Simple life, such as bacteria and microorganisms, requires chemical organization, membranes, replication, and available energy. Complex life, meaning multicellular life, needs additional steps, changes in the atmosphere, long-term environmental stability, and perhaps a series of contingent events. If life existed outside our galaxy, it is most likely that the vast majority would be microbial. Intelligent life, capable of technology, would be an even thinner layer. Terrestrial extremophiles force us to revise upwards the fraction of potentially habitable planets. It was once thought that life required a narrow range of conditions: temperate temperatures, surface water, and a moderate atmosphere. Today, we know that life can thrive in ice, in super salty waters, in extreme acidic or alkaline environments, under enormous pressures, or with almost no water at all. This means that worlds we previously dismissed may harbor simple ecosystems in places like underground environments, glaciers, or deep ocean floors. If we add up these data points, the picture is as follows: many galaxies with high metallicity, many stars with planets, a significant fraction of those planets in zones where liquid water is viable, at least during part of their history, diverse environments where organic chemistry can develop even before the planet forms, and organisms on Earth that prove life can adapt to conditions we once considered hostile. Under this framework, assigning an extremely low probability to extragalactic life becomes difficult to sustain. The big trap is confusing probability of existence with probability of detection. Even if there were millions of worlds with simple life scattered across the universe, that doesn't mean we can see them. For a technological civilization to be detectable, it must go through stages of biological evolution, develop advanced technology, and emit signals distinguishable from cosmic noise. Each of these stages may have a low probability. The total number of civilizations could be small, even if simple life is common. Moreover, technological civilizations have short timescales compared to cosmic timescales. A species may use technology for thousands or tens of thousands of years. The universe has existed for billions of years. This creates a kind of temporal mismatch. Many civilizations could have existed and disappeared before our own species appeared or developed instruments capable of detecting them. Temporal overlap is a critical factor. On the other hand, the methods we use today to search for life are focused on our own galaxy. We look for radio signals. We analyze the light from nearby stars passing through the atmospheres of planets. We study spectra in detail. All of this works, with great effort, at distances of tens or hundreds of light years. When we jump to scales of millions of light years, like the ones separating galaxies, our level of detail drops drastically. We only see the integrated brightness of billions of stars. Detecting the signature of a single planet in that sea of light is extremely difficult. Even so, statistics have something to say. If we take even the most conservative estimate, where only a tiny fraction of potentially habitable planets develop life, the result is still high when multiplied by the number of galaxies and stars. The margins of error are wide, but they tend to produce large values, not values close to zero. This suggests that life outside the Milky Way is not an improbable event in itself. What's improbable is that we can clearly identify it with current technology. Within the Milky Way, current methods are already at their limits. To study exoplanets, we use indirect techniques. We measure small variations in the light of a star when a planet passes in front of it. We detect oscillations in its spectrum caused by the planet's gravity. With great effort, we manage to reconstruct the approximate size of the world, its orbit, its density. And in some cases, we begin to analyze rudiments of its atmosphere. All of this happens at distances of tens or hundreds of light years. When we jump to millions of light years, these techniques become ineffective. In the extragalactic context, we do not observe a specific planet. We observe the combined brightness of billions of stars. Each pixel of the detector contains the light mixed from vast regions. The signal that could reveal the presence of an atmosphere with biosignatures gets diluted. Even if a life-bearing planet significantly altered its atmosphere, its contribution to the spectrum of the entire galaxy would be tiny, far below the observational noise. It's like trying to hear a whisper in the middle of a stadium full of people. Biosignatures, moreover, are not simple signals. It is not enough to see oxygen or water. We need to detect combinations of gases out of chemical equilibrium. Mixtures that, according to known physics, can only remain stable if there are active processes, like metabolism. Identifying these patterns is already difficult in relatively nearby exoplanets. It requires detailed spectra, high resolution, and many hours of observation. Doing the same with the integrated light from an entire galaxy adds an extra layer of complexity. Then there are conceptual limits. We define life based on the only example we know: carbon-based systems, water as a solvent, genetics organized in molecules similar to DNA or RNA. But the chemistry of an old and diverse universe could have explored different paths, different solvents, stable structures at other temperatures, forms of organization that don't resemble terrestrial biology. If that exists, it is likely that our current search strategies completely overlook it. We are fine-tuning instruments to find what we already know works here. This dependence on a single model creates a bias. We design telescopes, spectrographs, and algorithms to detect signals that we associate with terrestrial life. Oxygen, methane, ozone, liquid water, photosynthetic pigments. If life outside the galaxy uses other chemical pathways, it may remain hidden within what we interpret as noise or normal variations in the interstellar medium. Technically, we could be observing galaxies full of biological processes that we do not recognize as such. This is compounded by a problem of timescales. The light we receive from very distant galaxies left there billions of years ago. We see how they were, not how they are today. If during that time there was a brief phase with an intense biosphere on some planets, its chemical traces would have disappeared from the integrated signal. The total brightness of the galaxy does not retain that detailed memory. What reaches us is a kind of rough average over large volumes and long periods of time. Another important limit is the sensitivity of our instruments. Each telescope has a minimum signal threshold above the noise. To overcome that threshold, data is often averaged. Long exposures are integrated, and fine details are sacrificed. This averaging process is at odds with detecting weak and specific signals, like those that biological processes might generate on a few planets within a galaxy. The information exists, but it gets buried in a mix of much more intense lights. There are proposals to search for techno-signatures on a galactic scale. For example, advanced civilizations that modify large regions of their galaxy, build megastructures, or generate anomalous energy patterns. But these ideas are speculative. We don't know if technology tends to express itself in that way. We also don't know if such a civilization would want to be visible. Once again, we are working with a single model, ours extrapolated. So far, we have seen an uneven landscape. On one hand, a universe full of galaxies that massively produce stars, heavy elements, and planets. A physical framework where life seems possible in many places. On the other hand, a total absence of clear life detections outside the Milky Way. The contrast raises a direct question. What can we really expect from the future of this search? And what does it mean to speak of real probabilities in this context? The starting point is simple. Today, the observational situation is almost null outside our galaxy. We have not identified any unequivocal extragalactic biosignature. We do not know of any specific planet in another galaxy. What we do have is a robust theoretical framework, universal physical laws, stellar and planetary formation processes that repeat, organic chemistry present in gas clouds, and protoplanetary disks. Life on Earth appears early and withstands extreme conditions. All of that points to the idea that life should not be an exclusive phenomenon. The gap between theory and observation can only be closed in two ways: by improving our ability to see and refining the interpretation of what we see. In the coming years, both space and ground-based telescopes will advance on both fronts: larger optics, more precise interferometry, more sensitive sensors, increasingly detailed spectra of nearby galaxies, algorithms capable of analyzing vast amounts of data and detecting weak patterns that are currently lost in the noise. One possible strategy is to look for statistical footprints, not individual cases. Instead of identifying a specific planet in another galaxy, one could detect a slight systematic anomaly in the spectra of a set of galaxies. For example, a combination of gases that, on average, does not fit well with purely geological or stellar explanations. It would be a weak signal, but accumulated over many galaxies. It wouldn't provide a map of worlds with life, but it would be an indication that biological processes are active in more than one place. Another line of progress focuses on refining biosignature models, asking what combinations of gases, what emission or absorption patterns, what chemical imbalances might be generated by microbial life in conditions different from those on Earth. This includes scenarios with denser atmospheres, different solvents, and varying geochemical cycles. The idea is not to limit the search to a copy of Earth, but to cover a broader range of possibilities. The broader the catalog of plausible biosignatures, the easier it will be to interpret the signals from distant galaxies. Techno-signatures are also being explored. Signals associated not just with life, but with advanced technology, directed radio emissions, structures that modify the brightness of stars in anomalous patterns, traces of large energy engineering works. However, this enters an even more speculative realm. It assumes that many civilizations reach technology and use it in an expansive and visible manner. There is no guarantee that evolution will converge on something similar to our trajectory. Therefore, while it is an interesting avenue, it cannot be the main foundation for probability estimates. It is important to separate two levels of objective. One thing is to find evidence that life exists or existed outside the galaxy. Another very different thing is to communicate with it. Microbial life, even if common, does not send messages. It only alters its chemical environment. Even a technological civilization may not want to emit signals, or it may have disappeared millions of years ago. The probabilities of actual communication in human time are much lower than the probabilities of simple existence. Confusing both leads to unnecessary frustrations. Thus, when we speak of real probabilities of finding life, it's important to clarify what kind of discovery is in mind. Detecting a clear extragalactic biosignature would be a paradigm shift, as it would confirm that life is not exclusive to the Milky Way. It would not say anything about intelligence, culture, or technology. But it would be enough to dismantle the idea of singularity. On the other hand, establishing a dialogue with another civilization beyond our galaxy today borders on science fiction. The distances make it practically unfeasible. We must also consider a less spectacular but scientifically solid scenario. It could happen that we never achieve a direct detection of extragalactic life, but that by combining physical models, exoplanet data from our galaxy, and galaxy statistics, the scientific community reaches a strong consensus. A consensus in which the hypothesis, life is common, better explains the data than the hypothesis, life is unique. There would not be a concrete image of a distant world with alien oceans, but there would be a conclusion supported by well-understood numbers and processes. In that case, the change would be more conceptual than visual. Life would no longer be seen as an improbable accident, but would be understood as a possible, even repeated consequence of the chemical evolution of the universe. It would not mean that everything is full of civilizations, nor would it mean that the cosmos is a garden overflowing with complex life. It would mean something more sober. Given the size, age, and chemistry of the universe, the appearance of life in many different places is not only compatible with the physical laws, but also expected. The implications go beyond astrophysics. They affect how we understand our place in the cosmos. If life arose in many corners, our existence becomes part of a broad pattern. We are not the center of anything. We are a local manifestation of a general process. This does not diminish the value of human experience, but it does reframe it. Singularity stops being an argument of exception and becomes an effect of limited perspective. In the end, the real probabilities of finding life outside the Milky Way are caught between two limits. On the bottom, our current technological capabilities, which barely scratch the surface of the observable. On the top, a universe that seems to offer, time and again, the basic conditions for chemistry to organize into something we call life. Between these two extremes moves the research. Each new telescope, each new model, each new broad spectrum of a galaxy adds a small piece. The leap from the Milky Way to the rest of the living universe may never be seen in a single spectacular image. It may come as a slow conclusion, supported by accumulated data. What does seem clear is that as we improve our way of looking, the idea of a completely sterile cosmos outside our galaxy becomes increasingly incompatible with what we know. And the real challenge is no longer just whether there is life, but how far we will be able to recognize it when it finally leaves clear enough traces in our way of observing.